Hi there, folks. Today we're looking at angles of elevation and depression. And really, when we talk about these things, an angle of elevation is an angle that kind of increases or goes up from your perspective. And an angle of depression is one that goes down from your perspective. And what we're doing when we look at angles of elevation and depression is essentially we're analyzing things using right triangles. And we'll use trigonometry to find the different pieces of those right triangles, okay? So once again, an angle of elevation is the angle above the horizontal line representing the observer, and the angle of depression is the angle below the horizontal line representing the observer. And if you kind of think of it this way, think of like your eye line. If you stare straight ahead in front of you, your eye line is a horizontal line, and if you tilt your head up, that would be an angle of elevation. And so where you're looking, or something like a telescope, if you have the telescope perfectly horizontal, you see in a straight horizontal line, but as you tilt the telescope up, you're essentially forming an angle of elevation, and you're using an angle to observe higher, okay? Versus if you tilt the telescope down, that kind of thing. So kind of just thinking of it that way, we always do this from the perspective of horizontal line. As we increase the angle above the horizontal line, we're talking about elevation. Decrease it below the horizontal line, we're talking about depression, okay? For example, it says identify angles of elevation and depression. And again, you have to look at this thing compared to the horizontal line. And so when we look at this particular example, this could be from the perspective of a couple different people. So maybe we have a hiker that's up at the top of the mountain right here at this point. Maybe we have a hiker that is down at base camp here, who hasn't started their climb up. And of course, we have some people in this hot air balloon right here. And so as we kind of look at their different perspectives, if you look at angle 4 is from the horizontal line. That horizontal line represents the perspective of the person at the top of the mountain. And so as we look at this horizontal line, the angle is formed by going underneath the horizontal line, going down from that horizontal line. So angle 4 is an angle of depression, okay? So I'm just going to put a D here to mark that as an angle of depression, all right? When you look at the two angles from the hot air balloon, 2 and 3, angles 2 and 3 are both from the perspective of the people in the hot air balloon, okay? The horizontal line that we see go out in the middle of that thing, that's the perspective of the people in that hot air balloon. And so the angle above that right here is this angle goes above that horizontal line. That would be an angle of elevation. They're looking up from the hot air balloon towards the top of that peak. Okay, the angle 2 then would be an angle of depression. That's from the perspective of the hot air balloon. You're looking down, so the angle is looking down to the base of that hill or mountain or whatever it is. Okay, and then angle 1, again, this horizontal line down here, that angle represents, or that horizontal line represents the person at the base camp, and so the angle itself, when we look at this angle, is going up from there. All right, so that's an angle of elevation, okay? They would be looking up to the people in the hot air balloon, all right? And that's the idea of just angles of elevation versus depression. Really, it's about perspective, okay? We'll talk about angles of elevation and depression in terms of actual objects, like a plane or something like that. And if the plane is descending, we talk about in terms of an angle of elevation. They were up high, so their original position is represented by a horizontal line in the air. And as they descend, they're creating an angle that's on a downward trend, okay? When they're taking off, all right, the original horizontal line would represent like the runway, and their incline into the air represents an angle of elevation because they're increasing, okay? It's increasing from the horizontal, all right? And so for angles of elevation depression, we're going to use these to approximate values because, again, we're just forming right triangles when we do this thing. If I kind of scroll back up here, like if I looked at angle 1, well, angle 1, I could complete this thing with a right triangle right here, all right? And so we can find things, if we know angle 1, I could find this distance right here, and I could figure out how far up the hot air balloon is into the air, okay? Or something like this guy, because if I know the horizontal distance, all right? And so we're going to find these different values by essentially creating right triangles or viewing the right triangles created by the angles of elevation and depression, okay? And we'll use our trig functions, our trig ratios to come up with some of those things. For example, you're standing 53 feet from a wind turbine. The angle of elevation to the hub of the turbine, which is like the center of it where the thing spins, so the angle of elevation to the hub of the turbine is 56.5 degrees. If your eye level is at 5.5 feet above the ground, how tall is the turbine? And so again, if we kind of think of this, let me draw a quick picture. It's not going to be good. Don't get your hopes up. But if we have a wind turbine here, it has that center piece and then the blades that come off of that. Okay, that hub is kind of what we're talking about right here. It's this guy. It's that center piece that kind of is used here. All right. And so from that perspective, if we have a person standing on the ground, so we're standing on the ground right here, and it says basically their eye line right here, this is their eye line, is 5.5 feet above the ground. Okay, so this right here is a distance of 5.5 feet. But it says the angle of elevation from where they are to the wind turbine, well, it says that is an angle of 56.5 degrees. And the other thing is we know how far away this person is from the turbine. So right here, this right here is a distance of 53 degrees, or 53 feet, okay? And so if I kind of transfer that up to this triangle, that's 53 feet right here, okay? But when I look at this thing, I've basically formed a right triangle. So right here, this is my right triangle that I'm going to look at. Let me draw it more officially. And so as I look at this thing, if I know this angle right here in degrees, the 56.5, the thing I want to find is the opposite side over here. That's x is what I'll call it. And the thing I have is the adjacent side, which is the 53 feet. And so for this one, I can use my tangent to find that x value. And so for this one, I do the tangent function. So the tangent of 56.5 degrees equals opposite over adjacent. The opposite side is an x. The adjacent side is the 53. I almost read the wrong value there. And now I can cross multiply and solve for x. So I cross multiply, or I use my rules for proportions, my properties of proportions, and I get 53 times the tangent. Just forgot the rest of the letters of 56.5. Really, that becomes a job for my calculator. So here we go. Let me grab my calculator. So 53 times the tangent of 56.5. And I get 80.07. I'll just round it to the nearest whole, so I'll say 80 feet. And you have to be careful here just a little bit, because that is not the actual height of the wind turbine, okay? That is the piece of the triangle that I've found. And so right here, this is 80 feet. However, when we look at something like this guy, or maybe I should have rounded that to 1 decimal since the other piece is 1 decimal. So that was 80.1 feet, I believe. But when you look at that, that's only the distance of this top piece. I still have to include this piece down here. So yes, the side of that triangle is 80.5 feet, but the total height of this thing, if this is 5.5 feet, is actually 85.6 feet tall for the total height, okay? So I had to add that 5.5 feet that I wasn't accounting for, okay? That 5.5 feet is outside of the triangle that I was using to solve, and that's what makes this a little bit tricky, because that horizontal line is not exactly on the ground. If the horizontal line was on the ground, well, then I would have gone right to the actual height of the wind turbine, okay? So make sure you draw a picture. That's what really helps me find that I needed that 5.5 feet. Draw a picture. Make sure you have each of the little pieces. And understand that when you draw that triangle, you might not be finding the entire answer. You might just be finding the piece that's needed to find the rest of the answer, okay? If I look at this one, in order to land, a plane must begin a 3-degree descent starting from a height of 2,714 feet above sea level. If the airport is 1,007 feet above sea level, how far from the airport should the plane begin its descent? And so when we're kind of looking at this, and again, maybe I'll draw a quick picture here. I'll do a very childish version of it's going to look like a fish. That's not good. Okay, here's my plane. Apparently that's awful. That's really terrible. Nope, it looks like a fish, okay, but there's my plane, good enough, okay. So here's my plane. Apparently it's got a propeller. I didn't draw a very sophisticated plane, but anyway, it's got a descent of 3 degrees. So again, we have to look at the perspective of the plane. It's way up in the air here, and we want a descent of 3 degrees. And yeah, I've drawn that as larger than 3 degrees, but it's okay. We're going to mark it as 3 degrees. And obviously, we want to land at the airport, okay? We want to land on the tarmac safe and sound here. So here's my runway, and I want to land on that thing. So if I look at this, it says we want to have a starting height of 2714 above sea level, but the airport is actually above sea level also. And so, when you think about elevations are described, even though the airport might not be by the ocean, okay? We describe elevation in terms of how high any location is above sea level. And so when we think about this, if this guy is 1,007 feet above sea level, and the plane itself, we want to know when that thing is, we want to start this descent when it's 2714 above sea level. The question is, let's look at this piece of the triangle, okay? And so when we're thinking about that, we want the difference between, we want to know how far above the airport the plane is, okay? And so the idea here is the airport is 1,007 feet above sea level. If the plane is 2,714 feet above sea level, we actually have to subtract those two in order to figure out how far apart the airport and the plane are actually going to be in terms of the height. So the distance here for this guy is going to be 1,707 feet, okay? And again, that's the difference. When we if I draw a line that kind of cuts across here, we wanted to take this 1,007 away from this thing, okay? So now I have this triangle kind of completed. The question is, how far away from the airport should the plane begin its descent? And so, really it's a matter of which of these measurements we want. And I'm not an aviation expert, so I'm going to assume we want the horizontal distance, not necessarily the physical distance from the airport to the plane itself, that diagonal distance. So let's say we want the horizontal distance in terms of how far away this thing is. And so if that's what we're looking for, well, that means I would use the tangent here, okay? So once again, I could use the tangent of 3 degrees equals opposite, which is the 1707, over adjacent, which is the x this time. And of course, I could solve this in a lot of different ways. You could cross multiply and solve. I'm just going to switch the two diagonals in the proportion. And now this is a job for my calculator, okay? So I pull my calculator back up. I've got the 1707 divided by the tangent, 3 degrees. Okay, so I've got 32,571.5. And so that's the horizontal distance. If the question, or if what we really wanted to find was y here, if we wanted to find the diagonal distance, well, think about the perspective of that angle. That would be opposite and the hypotenuse that we're looking for. So that would be my sine function. So if I did the sine of 3 degrees equals opposite over hypotenuse. And once again, I could switch the diagonals to solve this, or you can cross multiply and solve. And again, plug it into the calculator here. So once again, 1707 divided by the sine of 3 degrees this time, and I get 32,616.2. That's feet, once again, okay? So again, it kind of depends on which of these we're looking for. I would assume it's the horizontal distance, but again, I'm not an aviation expert. Maybe they measure in terms of y, in terms of the physical distance, in terms of that diagonal. I don't know for sure, but either way, we can find either one of those using our trig functions in order to determine how far away we need to be before we start the descent, okay? But look at this guy. A plane takes off at an angle of 10 degrees and ascends to a cruising altitude of 32,000 feet above sea level. The plane is traveling at approximately 225 feet per second, so we're adding a little bit of speed in here, which we'll have to convert probably at some point as it ascends. If the airport is 1,500 feet above sea level, how long will it take to reach the cruising altitude? And so now we're kind of doing this in reverse. Now the plane is taking off from the runway. So once again, I can draw the runway here. My fantastic artistic skills. And now my plane is taking off from the runway. I'm going to draw my same horrible plane here. My little fish plane, because that looks great. Okay, it's got its little propeller there, so it's taking off. And so my plane is taking off once again. This is the perspective of the airport. This is a 10-degree increase. So again, I'm just forming this right triangle, and I want to know, hey, how long is it going to take to get up to cruising altitude? And here's the thing. Cruising altitude is 32,000 feet above sea level, but the airport is 1,500 feet above sea level. So again, when we measure the altitude of the plane, this whole thing is 32,000 feet. But this little piece right here is 1,500 feet. And so once again, it becomes a question of not how far the plane is above sea level. We want to know how far the plane needs to be above the airport, above the place where it started, okay? And so once again, I need to subtract those things. And so I don't want this overall measurement. I just want the piece of this triangle right here. I just want this height. And so when I subtract it, that's 30,500 feet. Okay? And so again, we just have to use a little bit of logic, a little bit of segment addition, really, when we kind of look at this thing. And that's what we're doing when we subtract. And so now from here, really what we need this time for sure, we need this guy over here. We need the hypotenuse of this. And the reason for that is because we want to figure out how long it takes the plane to travel from the airport up to that. Well, that's the physical path that the plane follows, okay? So we want to follow the actual distance the plane travels. Well, the actual distance the plane travels would be the hypotenuse of this thing. Okay, so once again, looking at that angle, I have the opposite side. I want the hypotenuse. Well, that's going to be my sine function. Okay, so once again, I do sine of 10 degrees equals opposite over hypotenuse. And once again, you could cross multiply to solve this, or you can use your rules of proportions and just swap those two diagonals. And now, once again, this is a job for my calculator. Let me pull my calculator up. Oops. And it looks like I get 175,642, and that's feet. And we'll just round it to 0.5 here, okay? But that's feet. That's the physical distance that this thing has to travel, okay? It's going to travel quite a long ways before it actually gets up to that cruising altitude, okay? But now the question didn't ask, how far does the plane travel? It says, how long will it take? And so here's the thing. If it takes that, if it's going to travel that many feet to get there, and we have the speed of this thing at 225 feet per second. This is how fast it's traveling, is 225 feet per second. I actually have to use a little bit of unit conversion to find the number of seconds here, okay? And so the idea here, really, if you can think logically, if I have the number of feet and I want to know the number of seconds it's going to take, I can just divide by the 225, okay? And if you want to think of this in terms of unit conversion, well, that would look like this. It would be 175,642.5. This is what you might do in science class, feet. And you want to do factor label here. Sorry, I should give myself a little space. Actually, let me do my factor label right here. If you think about this in terms of a factor label question, that's 225 feet goes with every 1 second. And so here, the 225 would go down here. That's feet. And the 1 seconds would go up here. The units for feet cancel. And now I can finish my factor label. But again, the idea here is that I'm just dividing by that 225. And that's what I see when I do the factor label. Okay? And so when I do that, I get 780.6. And that's in seconds. Okay? And you might look at that and say, well, seconds isn't a very good unit for measurement here. Maybe you want to take that 780.6 and divide it by 60 to get minutes. Okay? And see, now that's a unit that we can all kind of resonate with, all right? So 13 minutes approximately, okay? So I'll put that up here. So 13 minutes. All right? But a lot of different components to this thing. Again, we're setting up that angle of elevation and depression, which gives me a right triangle of some sort. We can use that right triangle and our trig ratios to solve for different pieces of it. Okay? And then once we have those pieces, we have to apply it to the context with which we're looking. All right? And be really careful, especially with the units that are given, especially when we talk about these examples of, above sea level, in terms of making sure you're getting the distance between the two things, not just the sea level like here. You had to do the 30,500. Sometimes you have to subtract some things. And we saw with the turbine example, we had to add some things at the end. So make sure you're drawing a picture, understand the context, so we're not missing any of those little pieces. Okay?